Hello everyone, we will start in a few minutes. Good morning or good evening to everyone. Welcome to this webinar. If you are registered, you are probably either familiar with Nonmem and you want to transition to Monolix, or you are already a Monolix user and you would like to translate all Nonmem runs. These are exactly the topics I'm going to cover today. So today I'm going to use 3 different examples, and for each of them I will show you step by step how to go from the Nonmem control stream to a Monolix project, including everything you need to know about the dataset format, the model implementation, and the overall workflow. The first example will be a simple PK model with covariates. The second one will be a more complex TMDD model encoded with ODEs. And the last one will cover what I will not cover in the 2 first ones, in particular transit compartments, inter-occasion variability, and handling BAQ data with the M3 method. And afterwards, I'm going to give you some practical tips and also tell you about what are the main advantages of working with Monolix compared to Nonmem. Before I start, 2 quick practical information. So if you want to ask questions, please use the Q&A box and not the chat. And the recordings will be available on our YouTube channel by the end of the week. So let's dive right away into our first example. So it's our simple PK model. Actually, it is extracted from this publication, which is a Nonmem tutorial. And it's a dataset for a phase 2A study with 60 patients. Each patient has received a single dose of an anesthetic over a 5-hour IV infusion, and we have 4 PK samples per individual. The model is a very simple 1-compartmental model with linear elimination, volume V, clearance CL, and a couple of covariates, age, weight, and sex. So that's a very good example to start simple. So that's how the dataset looked like, how it was used in Nonmem, and also how we will use it in Monolix. So we have a column C that actually contains only dots, so I can ignore it. Then we have ID, time, DV with my PK measurements, amount, rate, weight, age, and sex. And this is a Nonmem control stream. It's a bit small, so I'm going to zoom in into each part, and then we really will check line by line how to translate this Nonmem control stream into a Monolix project. And when I say Monolix project, it's really this concept of one project is actually one run in Monolix. All right, so let's first start with the dataset input. So here I see my dataset name and the different columns that will be used. Talking about dataset columns, actually, Monolix uses the same column types as in Nonmem, just with slightly different names. So ID would be also ID in Monolix, time is time, AMT we would call it amount, DV we call it observation, EVID we call it event ID, MDV we call it ignored observation. CMT is a bit special, I'm going to come back to it later. You can tag it in Monolix as either administration ID or observation ID. SS, II, and ADDL have the same meaning as in Nonmem with the same names. And rate, we would call it infusion rate. And then there are a couple of columns that are actually not reserved keywords in Nonmem, but that are commonly used. And they have a special column type in Monolix. So for example, if you have a DVID column to distinguish different types of observation, you would tag this column in Monolix as observation ID. If you have a flag to indicate samples that are below the LOQ, for example, BAQ column, you can tag it as censoring. If you have covariates, in Monolix you need to tag them as either being a continuous or a categorical covariate, or possibly a regressor if they vary over time. And if you have an occasion column that distinguishes several periods in time, you can tag it as occasion. And then there are a couple of columns that are really very specific to Nonmem that have no corresponding type in Monolix because it's not needed. So if I go back to my Nonmem control stream, let's see how to translate this into Monolix. So what I'm going to do is to actually go to the Monolix interface and show you everything step by step. So here, that's how it looks like when I start a new project. And the first thing I'm going to do is to load the dataset. So that's exactly the same dataset name. And then here, Monolix doesn't care about the column header names, but you can tag each of the columns with a specific column type. And actually here, all the tagging is done automatically because I have used typical headers. So once this is done, I can click accept. And actually, I right away have access to a plot of my data. So if I want to do exploratory data analysis, that's directly available here. Let's go back to the slides to see the next step. So the next step would be to select my structural model. And in this Nonmem control stream, it's done with the subroutine selecting model adven1 corresponding to one compartment with parameterization trans2 that corresponds to V and CL. And actually, we can do really the same in Monolix. So if I go back to the Monolix window and I go to the structural model tab, I can go to the libraries. And actually here you see that we have much more libraries than what is available in the Nonmem advanced routines. Here I have libraries for PK, PKPD, spatial PK, for example, with 2 different peaks, parent and metabolite, target-mediated drug disposition, time to event count, and tumor growth and tumor growth inhibition. So we have a lot that you can pick from. What I'm looking for is PK. And here I can filter at the top. So I have a model where I have actually an infusion, no delay, one compartment, linear elimination, parameterized with clearance. And if I select this model, it's the equivalent to selecting the adven routine that was used in the Nonmem control stream. If I go back to the structural model tab, I can actually see the content of the model. So I have this keyword longitudinal. Actually, I'm going to edit just to make it a bit bigger. So I see the input parameters, V and CL. Then I have this PK model macro that recognizes the V and CL input keywords and return the concentration that is then outputted here. And behind this PK model macro, we actually have the same analytical solution as what is used in Nonmem. The next thing I would like to highlight in this Nonmem control stream is actually this S1 scaling parameter that allows to divide the amount that is coming out of the model by the volume such that I get a concentration. And as we have seen in the Monolix model, actually this is not needed because I directly have the concentration as an output. In case you would like to use the scaling factor to actually scale the concentration, this can be done in Monolix too, but you would need to edit the model. As you have seen, you have the small edit button, and then when you enter in edition mode, you can actually add an additional line, for example, to calculate a CC2 concentration that would be equal to CC1 times 1000, and then actually here you would need to output CC2, my bad for the typo. All right. So we have already covered the dataset and the structural model. At the very top here, we have this problem statement where you can put some comments about what you have done. This is also possible in Monolix, and actually I'm going to make the video this a bit smaller so that you can see it. If I click on this icon, I also have a comment section. So here you can write one compartmental model, for instance, or anything else you want to record. Next topic I would like to discuss is these 2 lines here where we have defined the distribution of the parameters for the clearance and the volume. And I see from these equations here that actually these are 2 log normal distributions. If I want to define the same in Monolix, I would go to the statistical model and task tab. And here, that's where I define the distribution for each of the individual parameters. And I can select from a drop-down menu, and actually log normal is selected by default with random effects. So that corresponds to the same formula as in Nonmem. If I want to see the formula, I can click on this button, and actually we always show the formula in the log transform space if we have a log normal distribution. So here log v is equal to log v pop plus eta v, for instance. Then we have the two lines that define the covariate effects. And actually, to explain this a bit more in detail, I'm going to do that on the slides first. So in Nonmem, we actually have two different lines, one that defines the typical value with the covariate effects, and then the one that defines the inter-individual variability. Let's put them first all together by replacing TVCL here by the line above. And then what I'm going to do is to take the log of the clearance so that I get something similar to what I have shown to you in Monolix. If I do that, all the multiplication signs are going to be replaced by a plus, and I'm going to have the log of the clearance, that is log of theta 1, that is a typical value in the population, plus the effect of weight, that appears as theta t times log of weight divided by 70. This is this part here. Then I have the effect of age in a similar way. And actually for sex, what I had here was theta 7's power sex, meaning that if sex is 0, this term would disappear, and if sex is 1, I would have the theta 7. So here I've written it slightly differently with a bracket that indicates that this term is there if sex is equal to 1, and it's not there otherwise. And finally, the random effects. If I want to really explain you how it works in Monolix, I will show this really side by side. So that's the same equation as we had before with some coloring and the corresponding Monolix equation. And you see it's really the same, just the parameter names are a bit different because we use like more meaningful names than just theta numbers. So here I have log of CL pop plus the beta times log of weight divided by 70, same for the age. The parameter that is added if sex is equal to 1, and the random effects. What I'm going to do in Monolix is actually, in order to use log of age divided by 50 and log of weight divided by 70, I will create a new covariate directly in the graphical user interface that will correspond to log of age divided by 50. So let's see how to do that in Monolix. So here I have age, and what I do first is to add a new transformation of age. That is log of age divided by 50. Actually, that's not the name, it's a formula. I'm going to call it log th, for instance. And I click accept. And then once this is created here, I can click these two boxes to add this new variable on both the volume and the clearance. And it appears here in the equation that corresponds to the same as what I had on the slides. And then I'm going to do the same for weight. This time I divide by 70. And I also add weight. And finally, I also need to add the impact of sex. And then these big equations here are exactly the same as I had on the slides and exactly the same as I had in the Nonmem control stream. Let me go back to the slides. All right, so we have seen the first piece of the Nonmem control stream. Now I show you a second piece. And actually in the second piece, I would like to talk first about the error model. Here we have a proportional error model. I could also write it like this, for instance. If I want to implement the same in Monolix, I just need here in the drop-down menu to choose proportional. And when I do this, if I display the equation, I see that it is actually the same as in Nonmem. Here we call it dv as the name of the data, name of the column in the dataset, and Nonmem would call it y. And then our model prediction is called cc, and Nonmem would call it f. But at the end, it's exactly the same equation with a proportional error model. Then we have a definition of the omega blocks, and by defining the block, I can say, do I want just the diagonal terms or also a covariance term of the diagonal? If I want to define this in Monolix, I can use this correlation column here. If I tick the two boxes, then it means that I will consider a correlation between the random effects of volume and clearance, which is exactly the same as considering a covariance in the omega matrix in Nonmem. Here I have only 2 parameters, but if I have more, I could use a plus sign to create several groups, such that it would correspond to several blocks in Nonmem. Then let's talk about the initial values. First, the initial values for the thetas. So here I see that I have some initial values and also some values that are fixed. I can reuse the same values in Monolix, but I need to be careful that we have a slightly different definition between theta 7 and the beta that we have in Monolix. So our beta in Monolix corresponds to log of theta 7. So if theta 7 and 8 are fixed to 1, actually I would fix them to 0 in Monolix to have the same model. So if I do this in Monolix, I will go to the initial estimates tab and type in here the values. So the volume should start at 30, the clearance at 4. Here I said we can leave it to 0, and actually these values should be fixed. So to fix it, I click this button and select fixed. Here I have minus 0.1, and this should also be fixed. And here I have 1 and 0.75, and they are also fixed. So that would be the same as the theta definition in Nonmem. Next would be the definition of the initial values for the omega matrix. So let's first see the diagonal elements here, so the variance of the random effects, and also for the sigma. And actually I'm going to show this on the slide so that I can add some additional information. So first, remember that the random effects and for the random effects and the residual error, in Nonmem you define a variance, but in Monolix we work with standard deviations. However, actually for the random effects and the residual error parameter, you can just keep the default value, and in particular it's important to keep omega equals 1 in Monolix because this ensures a broad search of the parameter space. If you really need to fix a precise value because you don't want to estimate the parameter, for instance, you can calculate the omega that you would need in Monolix by just taking the square root of the omega that you have in Nonmem. And same for the residual error model. And then we need to discuss how to handle this covariance value here. And here again we have a small difference. For the off-diagonal terms, in Nonmem you define the covariance, while in Monolix we work with a correlation value, so a number that is between -1 and 1. Again, you can, if you want to estimate the value, you can just start from the default value of 0 in Monolix. That's going to work well. But if you want to fix it to a precise value, you can use this formula to get the correlation from the covariance and the variance values. And then the last piece of the Nonmem control stream is actually the definition of the estimation task and the covariance step. To do the same in Monolix, I would go to the statistical model and task tab and run here the different tasks at the top. So we have the estimation of the population parameters, and for this we have only one algorithm that is available in Monolix because it works very well for both simple and complex problems, and that's the SAEM algorithm. Then we have the estimation of the EBEs, so the individual parameter values. The conditional distribution has no real equivalent in Nonmem, but that would help us to sample different sets of individual parameters from the uncertainty distribution. Then we have the standard error task that would correspond to the covariance step in Nonmem, and the likelihood calculation and the diagnostic plots. So let me tick all those tasks and run. And actually you have a small warning suggesting me to save before I run, but I will just run for the moment. And actually I forgot to mention the... Okay, let's it finish and I'm going to go back to this afterwards. And the last thing that we have in the Nonmem control stream is the table statement, where you can decide what you want to put in the output tables. And actually this is something that is most of the time not needed in Monolix because we output all the typical values that are needed directly in the output file. So here you see the structure of the different output files that you get after run. And actually the individual parameters are in this file here, the individual etas in this one here, and in the prediction.txt we have the observations, the population predictions, the pred, the individual predictions, the ipred, and the residuals. If really there is an intermediate variable from your model that you also would like to output, what you can do is, for example, here to define the half-life, and then list this intermediate variable in the table statement within your structural model, and then this would create an additional table with those values, in case you need that. All right. So now that we have seen the input, so the Nonmem control stream, we also would like to have a look at the output, so the Nonmem report file. And what I see, so here I have again split it into several pieces. What we see at the beginning, for example, some general information about the version, about a small recap on the dataset. All this information, we also have it in Monolix, and it is available in the summary output file that you have generated automatically. And in here you can, for example, find here the version and find here the recap of the dataset. Then in the Nonmem report file we also have a section with the objective function value and the time needed to run. And actually this I'm going to show it to you in Monolix. So if I go back to my Monolix run, so it has finished, so I can close this. And I can go to the result tab, and that's really where I have all the results displayed as nice tables. So if I want to have an idea of the elapsed time, I can look here. Here it took a bit longer than the Nonmem run because I'm sharing the screen, etc. But otherwise you would have very similar run times for simple models. And then if I want to have a look at the likelihood value, it would be here, and here I can see the objective function value. In Monolix we only report the value with the constant. Remind this if you want to compare to the Nonmem value. Then in the Nonmem report file I would have the final parameter estimates that would be displayed like this. In Monolix that's much easier to read. If I go to the popparam tab, I can see here the name of the parameter and the estimated value. Now the question is, did we actually get the same estimates? And to look at this, I have put here a table of the value that was estimated by Nonmem. Then I have converted it so that we can work with standard deviations on both sides and compare what is comparable. So that would be the transform values estimated by Nonmem by taking the square root of the variance to get the standard deviation, and that's the Monolix values. And we see that the values are pretty similar but not exactly the same. And this is expected because we have used different algorithms, and in addition the SAM algorithm is a stochastic algorithm. But the values are pretty close, and also in terms of likelihood, with Monolix having a slightly better likelihood. Then the next step of the Nonmem report file would be the standard error of the estimates. In Monolix they are displayed in this same table with the standard error and relative standard error too. And when there is no value, it's just because the parameter was fixed. And here we have a color code that highlights the high RSEs. And here I can see that my correlation estimate is pretty uncertain. And next comes the diagnostic plot. So if you want to have a look at diagnostic plots in Nonmem, you would have to use a third-party software such as Expose, Piranha, Kiwi, or PDXPOP, for instance. And what is really nice with Monolix is that all the diagnostic plots are built in. So I have really just run, and at the end of the run, I have really a nice set of diagnostic plots that are generated by default and that can be highly customized also. So here I have the individual fits, for instance, the ops versus spread that I could have a look on log scale. All the plots are interactive, so if I click on an individual here, I can find it again in the individual fits or in the scatter plot of the residuals, etc. And I also have a VPC plot, which looks pretty nice here, for instance. Then you may also want to run a bootstrap, so that would be an alternative to get an idea of your confidence of your estimated parameters in case the covariance step fails in Nonmem. This can also happen in Monolix, that actually the standard errors don't fail completely, but some of the values are none because Monolix didn't manage to estimate them. In that case, going with a bootstrap can be an alternative. In Nonmem, you would use PSN to do that with this kind of input command, for instance. In Monolix, we have all this included in the graphical user interface. To show you some results, I'm going to load a project that has already run. If I go here to the Bootstrap tab, that would be all the settings I can choose to run the Bootstrap, and then I have all the results that are displayed as tables with the summary metrics and also as plots. It takes a bit of time to appear because I have just loaded the project, but here you would have histograms, for instance. If you want to do a covariate search, in Nonmem you would also go via the third-party software PSN, for instance. Here that would be an input file with a configuration for SCM approach, so really a stepwise addition, forward and backward addition and deletion, where you can define what you want to try. And we have something very similar in Monolix 2. Here are the plots. So if I go back here and go to model building instead, here I can really choose different strategies to do my covariate search. So we have the typical SCM, but also faster ones. Here I can choose which covariates I would like to investigate or fix, etc. And then I'm going to have all the results displayed as a table that really highlights what has changed from one run to another one. And then there is an option that is pretty rare in Nonmem, but more used in Monolix, and it's this parallel retry that allows you to do several runs from different initial values. And in Monolix, this would be what we call the assessment. And here you can really, for example, do 10 different runs. Each run would start from a different set of initial values that are picked randomly within this interval. And then the results would look like this, where you can really see all the trajectories. And this is a good way to assess the stability of your runs. For example, before starting a covariate search or from time to time in your modeling workflow. So that was a bit an overview of the different steps of a Monolix workflow. So to do a short intermediate recap, in Monolix you would start by loading your dataset and tagging the columns. You can right away after this step have a look at your data. Then you can select a structural model, and we have a large library of pre-implemented model, and you can also write your own. Then you can choose the initial values. What I have shown to you before is to choose values by yourself, typing the value, but we have also a very nice display of those with the auto init button that does a pulled fit to find good initial values. Then you define your statistical model. And then you can run, and you really have all the results directly in the graphical user interface so that it's really convenient to interpret them. So that was our first example. Now let's have a look at our second example that is a bit more complex, and it's a TMDD model. I have taken this Nonmem control stream for this publication. Actually, the Nonmem control stream was in the Nonmem to MRGSolve R package. I have slightly modified it to squeeze in additional features that I wanted to show you. And for the dataset, I have simulated it using Simulix, using the same design as in the publication. So we are looking at a drug that is called evolocumab. It's a monoclonal antibody against PCSK9 that is meant to lower cholesterol levels. We have a phase 1A with healthy subject, single ascending dose, and a phase 1B with patients that have received a dose either every week, every 2 weeks, or every 4 weeks. The model is a target-mediated drug disposition model with quasi-steady-state approximation that captures the total drug, the free target, so PCSK9, and the cholesterol levels. That's how the dataset looks like. So we have things that are a bit new compared to the previous example. In particular, we have ADDL and II columns that are going to be handled exactly in the same way in Monolix. We have a CMT column that distinguishes the different types of observations of the DV column. MDV and EVID, and then we have a dose group and healthy binary 1 or 0. So let's do the same and proceed step by step through the Nonmem control stream. So first we have this input line that defines the meaning of the different columns. And that's going to be pretty similar in Monolix. So I'm going to add ADDL as additional doses, II as interdose interval. Here CMT is used to distinguish different types of observations. So I call it observation ID, MDV ignored observation, and EVID event ID. A small note on the CMT column. So if CMT in Nonmem is used to just distinguish different types of observations, then you tag it as observation ID. If it's rather used to distinguish several types of doses, for example, an IV dose arriving in the central compartment and an oral dose arriving in the depot, then you can tag CMT as administration ID. If it is used in Nonmem for both, then you would need to duplicate it outside of Monolix, such that you can tag it once as ADM ID and once as observation ID. Then the next thing that is new in this Nonmem control stream is this ignore statement that allows me to ignore all lines where the dose is equal to 0, so that's actually the placebo individuals. And actually I'm going to show you how to do that directly in Monolix, and for that I'm going to load the project corresponding to this second example that I have already prepared. If I go to the data tab, once you have loaded your data, you can have access to the filters, and here you can create an additional filter, and here you can remove or select lines or individuals, and here I have removed the lines for which dose milligram is equal to 0. So that corresponds exactly to the same as what has been done in Nonmem, and then you can combine several filters with union or intersections. So this gives you the flexibility you need. I have a small note on those filters because that's going to be something that is a bit complicated at the beginning. Before you can use a column to filter, you need to tag it as a specific column type in Monolix, and each column type has specific constraints. So if you tag your column as categorical or continuous covariate, as I have done for the dose milligram, then it needs to be constant over time with each individual or each occasion of each individual. So this means that you can use this type of column to exclude an entire individual, but not just to exclude a single record. Alternatively, you can tag your column as a regressor. The constraints for regressors are that it needs to be a numerical value, and be careful that if you have a dot, it's going to be replaced by the value on the previous row of the data set. And it also needs to have the same ID on all lines that correspond to the same ID and same time. So for example, if you have both PK and PD data that are recorded at the same time points, and you want to exclude only one of the two, that's not going to work. In that case, what you can do is actually to modify a bit your data set to actually have your exclusion flags really as separate columns. So in that case, you would have one column for each reason, and each column you have an integer value that is 0 if you want to include the line, or any other value if you want to exclude it. And then if you tag this column as ignored line, actually you don't need to go through the filters, it's already filtered directly when you tag your data set. All right, next topic is about the subroutines, and here we have this advanced 13 toll 6 that indicates to use a stiff ODE solver with this tolerance. And I'm going to go in more detail into the entire model afterwards, but really about this specific point. In the Monolix model, if I want to use a stiff solver, which is not the default, then I would add OD type equals stiff. And if I want to change the relative tolerance of the ODE solver, I can write ODE rel toll and then the value. Actually, 10 to the power minus 6 is the default value, so I would not need to add it in this example. Then the next part of this beginning of the Nonmem control stream is the definition of the different compartment, and actually this is not needed at all in Monolix. We work with ODE variables, and there is no need to define the compartments in addition. So this can be just skipped completely. That's a continuation of the Nonmem control stream where we define the parameter distribution. So here I have a log normal distribution, and here I have a actually logit normal distribution with this small transformation. If I want to handle this in Monolix, I would like select from the drop-down menu, and that's what we have already seen before actually. So we have log normal, logit normal, normal, and probit normal that is available in the list. In this example, I've squeezed a bit an additional feature. I have a distribution for the clearance that is actually not one of those that I have listed just before. In this example, I have a proportional distribution for the clearance. If you want to, I would not recommend doing that because it does not ensure that clearance is positive, but if you really want to do it, you can do it in Monolix by actually separating the fixed and the random effects. So you would have in your model that you need to write by yourself, the CL pop that corresponds to theta 3 and the eta CL that corresponds to the etas. And then you would reconstruct the clearance from these two input parameters exactly in the same way as in Nonmem. Then you need to be careful in the statistical part of the model definition in Monolix. You need to make sure that CL pop has no random effects because it represents only theta 3. And that eta CL is defined with a normal distribution because it represents just the random effects with random effects. And then in addition, eta CL is actually a centered normal distribution around 0. So I need to fix its value to 0. So that's what we have seen already before, how to fix a value. And that would be, it would be the same procedure if you have a box-Cox distribution, for instance. Then we have a part with categorical covariate. So we have already seen one way to code it with sex, and now it's a bit different. I have an if statement so that I have two different typical values if the healthy is equal to 0 or to 1, so for healthy and patients. And actually the way to do this in Monolix would be to just add healthy as a covariate on PCSK9 as we have done before. And in that case, in the results, I would actually see the typical value for PCSK9 that corresponds to the patients, and then the beta that corresponds to the offset I have in case I have healthy individuals. And if I tick this display fixed effect by category, I can actually recover what is the typical value for healthy and patients, so that would correspond to the two theta values I have in the Nonmem control stream. So the coding in the background is a bit different, but in terms of display of output, I can have the same as in Nonmem. And then I have here a bit also a different example compared to what we have seen before. So here I have the effect of dose milligram, that is a continuous covariate, on the bioavailability. If I go to the next slide, if I want to implement this, actually, I cannot do it directly in the graphical user interface. We have seen in the graphical user interface that we can easily either have an exponential relationship or a power law relationship on a log normally distributed parameter, but that's not our case here. So if I want to implement something like this, and it would also be the case if I want to implement a time-varying covariate, for instance, then I need to tag my dose milligram column as a regressor instead of having it as a covariate. And then I need to implement its impact directly in the structural model. So in the model, I would list dose milligram in the inputs. I would then list dose milligram use regressor so that I indicate that it's not a typical parameter to estimate, but it's going to be read from the data set. And then I just write the formula as I have here. And I need to be careful that D50 is now a more population parameter that has no inter-individual variability. So I need to make sure that I have no random effects here. So that's really a general solution that if you cannot implement what you want directly in the graphical user interface in terms of statistical model, you can always go through the structural model. Then what is also new in this model is that we are using a bioavailability and a lag time. And actually here F1 is going to be applied to the dose that arrive in compartment 1 with a bioavailability and a transformation for the units. And same for and then for lag time. And actually, we have something similar in Monolix using the depot macro. So the depot macro will be used to link the doses in the dataset to the model variables. So here what it is saying is that I'm going to read all the doses that have administration identifier equals 1. So that's the case by default if I have no DMID column. And I'm going to apply those doses to the ODE variable A1. All those doses, I'm going to multiply them by this P parameter. So P is a recognized keyword. And then I write the formula I want to use. So that's going to be the bioavailability I have defined above and my unit transformation. And I will also apply a lag time. And here again, T-lag is a recognized keyword. If I want to use a different name with, for example, here capital letters, I just write recognized keywords equal new name. So that's going to really be the way we make the link between the dataset doses and the model. And you see that we don't need the concept of compartments. We really just say the ODE variable name on which we want to apply the dose. Then the next part of the Nonmem control stream is just a couple of parameter transformations. And this will be exactly the same in Monolix. In your model, you can really just define any arithmetic formula you want. And then comes the ODE system. So in the ODE system, we have the initial values, then we have a couple of intermediate variables, and then the time derivatives themselves. And actually, it goes in a similar way in Monolix, but we have a few syntax differences. So in Monolix, we can actually use any variable name. And for example, here I have used the A1 to keep something similar to Nonmem, but you really don't need the parentheses. And here I have called it A1, but it could be a drug, for instance. For the initial value, we would use the name of the variable _0. For the time derivative, we use DDT _ the name of the variable. For square root, log, exponential, we would use small letters. And for the power sign, we would use the small hat. But this means that most of the time you can just copy-paste your Nonmem equations, do a couple of replace all to adjust for these syntax differences, and then you're done. Then the next topic I would like to discuss is this if statement I have here that allows me to define the inhibition term. And actually this is again similar in Monolix but with slight differences. So my if statement in Nonmem actually will be converted to a if and in Monolix with small letters. The greater than 0 with letter will become the above sign 0 and time will become t. But then I can have something really similar. And actually in this example I do not need this if else statement in Monolix because my ODE variables are defined at any time, including time 0, so I don't need to make the distinguish of time 0 or afterwards. Then comes all the error block, where I will first focus on the mapping of the model output to the different compartments. So here I have these if statements on the compartment value 2, 3, 4 that define different hybrid values, and for one of them I have a unit conversion. And then I have the definition of some 0-1 binary values to then define the output y. And actually this is all much simpler in Monolix. If I want to do some Unix transformation, I can do it in the model. And then in the output line, I just list everything that corresponds to an observation in the dataset. And then the mapping is done in this panel here. In this column, I find all the model outputs. And in this column, all the values that are in the observation ID. So in my case, the CMT column. And then I can draw lines to connect those points and say what goes with what. Then there is something that is also defined here. It is all the definitions of the residuals. And actually this is not needed at all in Monolix. It's going to be calculated automatically because it's actually the same information as we have in the residual error model. So this we can just skip. Then comes the residual error model. And here we see that we have for each of them actually a combined model with a proportional term and a constant term. And actually remember this formula here for the weight, that is actually the same as what we would have here in the error model. if I do the same in Monolix, I would just select from the drop-down menu the combine 2 model that, if you look at the formula, actually corresponds to the same as what we have in Nonmem. Then we have the initial values. So that would be the initial values for the theta's. That would go as we had before with bioavailability that is fixed. Then we have the initial values for the omegas. What I want to say here is that here we have some omegas that are fixed to 0. Actually, in Monolix, it's not possible to fix an omega to 0. If you want to do the same, you just remove the random effect, and that's actually the same. So that's what I have done here for KDEG, for instance. And then we have the estimation task and tables. In Monolix, you would mostly look at it in the graphical user interface because it's much easier to understand what is going on here. And again, you have all the plots available too. All right, so this covers our second example. And now in the third one, I'm going to show you really a bit more some more specific features that I could not cover in the 2 first examples, in particular inter-occasion variability, BLQ data, and transit compartments. For the third example, I have actually taken it from this publication on the rifampicin. So I found the Nonmem control stream in the supplementary material, and I have again simulated the data with Simulix. So the drug is rifampicin that is used against pulmonary tuberculosis. And it's an open label phase 2 multiple dose rising trial with tuberculosis patients that have received a daily dose over 14 days. And we have dense PK sampling at day 7 and day 14. The model is actually pretty complicated. So we have here a 1 compartmental model with nonlinear elimination with a VMKM Michaelis Menten. We have auto-induction of the elimination that you see here with this enzyme. We have an absorption with transit compartments. And we have inter-occasion variability between day 7 and day 14. And we have also data below the LOQ that is handled with the M3 method in Nonmem. So let's see this step by step. So again, let's first have a look at the dataset. So we have all these columns in the dataset that actually looks like this. So what I would like to highlight is that we have this LNDV column that is a log of the concentration. I have a BLQ column that tags with the data that is below the LOQ. And here I have put the LOQ value in the LNDV value column. That's how it should be done in Monolix. Have the amount, EVID, the occasion column that tags with 1 day 7 and number 2 day 14, and then a couple of covariates. So in terms of column tagging, what is really important is to tag my BLQ column as censoring, and that's actually the only thing you will have to do in Monolix. And here I have tagged the occasion column as occasion. So if I continue in the Nonmem control stream, I have here a couple of covariate effects. So the effect of the fat-free mass on the Vmax and V2 parameter. This is something we have already seen before, so I could just do a transformation of the fat-free mass to get a power law distribution, add it on Vmax and V2, and then fix the coefficient. And then comes the interesting part about the inter-occasion variability. So here I have an if-else statement to distinguish the 2 different occasions, 1 or 2, and I defined IOV Km as being either theta 11 or theta 12, depending if I'm in occasion 1 or occasion 2. And then I can use this term to define the distribution for Km that has actually IIV term, eta 1, and the IOV term. So here I have an example with 1 parameter with just IIV, 1 with IIV and IOV, and 1 with only IOV. And this again is much simpler in Monolix, because once you tag your occasion column in the dataset, you're going to see it appear in the graphical user interface. And then you can just tick the box to decide if you want inter-occasion variability or not. So here Vmax has only IIV, Km both, and the bioavailability only inter-occasion variability. And that's it. And this means that you can have like also many occasions over time, and it's still very easy to implement. Then comes the part about the transit compartments, and this is also pretty cumbersome in Nonmem. All this code is needed to define the transit compartments. So actually I have an analytical solution here, but that requires some intermediate variable, and in particular you need to write the approximation of the gamma function, the time since the last dose, etc. In Monolix, this is again much easier. The only thing I need to do is in my depot macro that links the doses to the model, I can use two additional keywords, KTR, the transit rate, and MTT, the mean transit time. Here I have defined KTR from NN, the number of compartments. And MTT, I wanted to have its capital letters in the input, so I just do MTT reserve keywords equal new parameter name. And that's it. I don't need to do anything else. All the same analytical solution will be used in the background. A small note, however, is that in the Nonmem code, in your ODEs, you would have the rate of transfer that appears in the equation from depot to central, and this is actually not needed in Monolix. In Monolix, you would here define as a target directly the central compartment. The Ka parameter goes into the depot definition, and then when you look at the concentration in the central compartment, you just write the elimination term. Everything related to the input is defined already here. Then you can have the calculation of the hype rate, that will actually be the log of our concentration to map what we have in the dataset, with a small safety to avoid taking the log of 0, which is undefined. In Monolix, you would do exactly the same, and then output log of the concentration. When you define the residual error model, here we have a constant error on the log transform value. I would do exactly the same in Monolix, selecting constant from the drop-down menu to end up with the same equation as in Nonmem. Then comes the part on the M3 method for the BLQ, so that really allows you to take into account the likelihood of having an observation that is below your LOQ value. And to do that in Nonmem, you need to add all this code, so to have a flag that tells you that in the Y column you're going to put the likelihood value and not the prediction, and then calculate the likelihood value by yourself in those equations. And actually that's, again, much simpler in Monolix. The only thing you need to do is to tag your BLQ column as censoring, and then you're done. All the stuff related to the likelihood calculations will be done automatically in the background. Small note to go back to the IOV. In the omega block, we had in the Nonmem control stream, we have this same statement to make sure that the two etas that corresponds to IOV have the same value. Actually, this is not needed in Monolix because by default, Monolix knows when you define IOV what goes with what. And then we finally have the estimation task and tables. And in Monolix, you would just click the Run button and have all the results displayed in the graphical user interface. So this was really 3 concrete examples showing you really step by step how to transfer the Nonmem control stream to a Monolix project. Now I'm going to go back to a few practical tips. So first, a few practical tips about BLQ dataset, BLQ in the dataset. So it's when you use a BLQ tag, it's convenient to have only 0 and 1 values in that column, with also 0 on the dose lines, like we have in this example, such that then you can tag this column as either ignored observation, and then you would use M1 method, or you tag it as censoring, and then depending if you have a limit column or not, you would use M3 or M4 method. Remember that in the DV column, you need to have the LOQ value here when sense is equal to 1. Then the second topic I would like to stress is this ADM ID column that allows you to distinguish several types of administrations. It's really more clear in Monolix if you really have your dedicated ADM ID column, although in some cases you can reuse the CMT column that you already have. And if you create a new column, what is nice is to put number 1 for IV and number 2 for extravascular. And that's not mandatory, but that would allow you to easily use all the models from the library, so that's convenient to use this convention of numbers. For regressors, we have a different convention in Nonmem and in Monolix. In Nonmem, when you have a variable that varies over time, in between 2 points, it would use the next value carried backwards. So here between time 0 and 7, AUC tau would be 5.5. In Monolix, we do the opposite. It is the last value that is carried forward. So if you want to really have the same values between time 0 and 7 in both cases, you need to shift all your values by 1 in Monolix compared to what you had in Nonmem. Sometimes it does not matter, sometimes it does. Depends what your column is about. In terms of units, as you have seen, we don't really have a scaling factor as we have in Nonmem. You can add it by yourself in the model, but it would need you to edit the model, and that can be a bit cumbersome if you want to try many different models. So it's better to have the same units for amount and DV in your dataset, such that you can use the library models directly without having to edit to add the scaling factor. You can also think ahead about how you would like to stratify your plots. Any variables that you may want to use to stratify your plots, be careful to tag it as a categorical or continuous covariate when you tag your dataset. Here, for example, I have a dose group column. Tag it right away as categorical covariate, for instance, so that you can then easily stratify your plots once you get your results. For time-varying covariates, that's something I haven't touched much yet. We have two big options. So you remember that in Monolix, if a covariate needs to be constant over time, so a time-varying covariate cannot be tagged as a covariate. One option would be to create just two columns, one that would be the baseline that is constant and that you can tag as a covariate and then use in the automated search procedures, etc. And then the second one that varies over time that you can tag as being a regressor, so that you can use it for a custom model implementation directly in the structural model. So that's option one. And option two would be to say, actually, my covariate needs to be constant over occasions. So what I can do is to add an occasion column. So here I've added occasion 1 and occasion 2, such that the covariate is constant within each occasion. And then I can tag it as a covariate, handle it in the graphical user interface, and have it also available for automated covariate search procedures. Second point is about exclusion flags. For example, if you have a C column. So I have already touched a bit on this when I talked about the filters. So first, make sure that your column has only numbers and no dots. If your column here, for example, the C column, has the same values on all lines corresponding to the same ID and same time, and be cautious, that's not always the case if you have several DVID. But if it's the case, you can tag it as a regressor, and then you use it in the filter tab. And then you have all the flexibility to filter only value 1 or only value 2, etc. Sometimes this is actually you have several observation ID at the same time for the same individuals, and you want to exclude only one of the two. In that case, it's actually easier to prepare several columns that correspond each to a different reason. For example, here 1 is actually an outlier, and then all these 2, I want to exclude them because I have a missing amount. In that case, I create one different column for each reason that contain only 0 and 1 values, and then I can tag this column as ignored line. This would be a second option. Now a couple of tips regarding the workflow. So really, if you can implement your model in the statistical model in the GUI, really that's a better option because it's faster and more stable. And do the implementation in the structured model only if really needed, for instance, for time-varying covariates. When you run, really don't forget to do a save as before you run. Otherwise, you might overwrite or lose results. Then, if you need to modify your dataset, really be careful that you save your new dataset under a new name. Otherwise, you're going to have problems when you reload previous projects. So if the header structure is unchanged, you just have added additional lines to your data set, for instance, then your project will reload but without the results. So that's a bit would be a bit sad. And actually this makes sense because we really want to make sure that the results we show corresponds to the data set that you currently have, which is not the case anymore. Or second option, if you have actually added additional columns in your project, the project will not reload at all and you would have an error like this. So really it's much better if you do a dataset modification to save under a new name such that your old projects still remain valid. Then remember that the SAM algorithm we use is a stochastic algorithm. So it's really important to assess the stability of your results using the convergence assessment, as I have shown before. And that's in particular the case if you want to start a covariate search, you really need to make sure that the likelihood value you get is sufficiently stable to see a difference of 4 or 5 points from one run to another one when you add a covariate. So really make sure that you check this from time to time. If you want to use several functional forms for covariates, remember to prepare them in advance, exactly as I have shown to you in the first example, and then they will be available in the automated covariate search procedures. And finally, a same structural model file, if you have defined it by yourself, not from the library, as I have done for the TMDD model, can actually be used by several Monolix projects. So if you modify it, be careful that it might also affect other projects. So here too, it's better when you modify to just give it a new name. All right, so this was a couple of tips. And now the last thing I would like to talk about is a bit what are really the advantages of working with Monolix rather than with Nonmem. So I've listed 6 of them. So the first one is that we have an easy to use graphical user interface with a clear display of results. Second, we really have a large library of pre-written models, which means that most of the time you can just pick a model from the library, so there is no coding mistakes, all these models are validated. Or if you need something more custom, you can take it from the library and then edit it a bit. For example, for my TMDD example, I have shown to you how to write it by yourself, but you could have picked it from our TMDD library and then added just the line corresponding to the cholesterol model. We have all the tools in one application, the Monolix. So all the diagnostic plots, if you want to do a bootstrap or covariate search, it's all included in the graphical user interface in one place. In case you do a mistake when you define your model, we really provide clear error messages that help you to understand what is going wrong. So you are not stuck like, I don't understand how to continue. Our ODE solvers are very efficient, which means that if you have a complex model, what our users report is that they very often get shorter runtimes in Monolix compared to Nonmem, especially for complex models. And finally, we have a really simple implementation for BLQ, inter-occasion variability, and transit compartments, which make it really easy to use these features compared to what it would have been in Nonmem. So if I want you to remember 3 take-home messages. The first one is that actually translating your Nonmem control stream to Monolix is pretty easy. I really have covered most of the cases you can encounter in this video, so you should be all set to do it now by yourself. You will need to adapt a little your workflow. We don't work in Monolix exactly in the same way as in Nonmem, but once you have adapted, and that's going to be not that hard, you will really gain a lot in productivity because Monolix is really easy to use. We have an integrated workflow, everything in one place. If you would like to know more about Monolix, you can visit our online documentation where we have a lot of written information and also video tutorials. And what we're going to add soon is a Nonmem to Monolix documentation that will really be a recap of everything I have shown today. So that's coming soon. Thank you very much for your attention. Have a nice day.